So now you found a bunch of literature, and it's time to start reading it. So the main reason you want to do that is, of course, the same reason you were looking for literature in the first place. You need to know who came before you and what they did. But it's absolutely true that no one has time to read and truly absorb all of the papers that come out every single day in astronomy. There's a phenomenal avalanche of papers. So you have to pick and choose what you spend time on. To some extent, it's sort of like choosing which stories you read in a newspaper if you're low tech, or on a news website, or in a news app if you're more recent tech. But the idea is no one really reads every single story in a newspaper or on a website. You pick and choose what you want to read depending on what your interests are. This is in contrast to what you might do for a magazine, where you really would sit down and read every article cover to cover. So when you read a paper, you probably have either of two goals. The first goal might be to really understand in detail what it is that they did and what they're concluding about it. And some examples of that might be that it's a paper that's really close to the kind of science you do, or it's written by a collaborator or a colleague that you know does really good work and you want to learn what they did, or you're responsible for presenting it at a journal club, or some other reason where you really want to understand it in great detail. The other goal that you might have is to just get their big points and get the data out of their paper. So that would be the case if you just needed the data to do your own science. In that case, you need to know the basics of what it is they're presenting, what columns are what, and how they got the things that they put in the table. But you don't really need to know the details of what they did with that table as much as you just want the data table. So the either way, you want to have the same basic first approach to the paper, which would be look at the title, look at the authors. If it still looks interesting, read the abstracts. Now, abstracts tend to be pretty dense, but they do summarize the big points of the paper. You can read the abstract directly from ADS if you're looking in ADS, or in Simbad if you're looking in Simbad. You don't have to even download the paper to decide to get this far. And I just want to point out that different journals have slightly different conventions when it comes to the abstract. So this is an abstract of one of my papers, and just to model it, you first want to look and see, okay, it's a recent paper, right? Because it came out in 2015, October. And then you want to look at the title and the authors. In this case, you might read the title and think, okay, giants, that may be not what I'm doing. But you look at the authors, you go, oh, I know some of those people. Let's read the paper and figure out what it is that they did. There's the abstract, of course. That abstract is actually kind of long compared to what abstracts are supposed to be, but this was a complicated study that had a lot of subtleties, and so that's why the abstract is long. The other thing to note in the abstract page is that in this case, it's explicitly saying, look, there's a machine-readable table. That means that there's a big data table, at least one, in this paper. So if you are coming at this in the perspective of, I just want to harvest the data, that's a good thing to note. Now, this is an abstract from a European journal called Astronomy and Astrophysics, and some time ago they made a conscious change to ask authors of papers that appear in ANA to actually write an abstract that has these main headings. The yellow is mine, just to call your attention to them. In the journal, they're just a different font and italic. But the whole point is that they want a context, the goals of the work, how they approached it, the big results, and then the conclusions. So these abstracts tend to be longer than the abstracts in the American journals. So the abstract, of course, is going to, good abstract should summarize the goal of the work and the approach to the work and the main conclusions that come from the work. If you still are interested after you read the abstract, then it's up to you to decide if it's worth your time to go further. So if you decide you do want to go further, then you need to get the PDF of the article. If you can't get it easily from the journal, you should try AstroPH, because as I was saying before, all the content is the same, even if the typesetting isn't the same. Or if you're having trouble, I can get you the PDF. So when you first are holding the paper in your hands or looking at it on the screen, the first thing you want to do is look at the figures. Often, the first figures of the paper are sort of a roadmap. They give you some sort of an orientation, such as this is where we're working, or this is where we have data, or a crucial plot that says this is the new parameter space we're employing. It's not always the case, but usually the first figure, sort of gives you a lay of the land. The other thing to remember is that people only go through the trouble of adding figures if they think it provides something important. If it's less important, they'll describe a figure in the text but not include the figure in the paper. And good authors, because they know that you're coming at these papers looking at the figure first, you want, as an author, to put the point of each figure in the caption. So the caption should define colors, shapes, lines, notation, whatever is happening in the figure. But then it should include the reason why they added the figure, or the point that you're supposed to take away from the figure. And the later you go in the paper, the figure should have more and more import, because that is, at the end of the paper, is where they're making their main points. And so those figures should be the most important of the work. So here's a figure that came out of that paper whose abstract we were looking at earlier. And it first defines the symbols. So it says it's a 3-color image of this target, which is at about an arc minute on a side and north is up. Then it says what wavelengths are the color planes. Blue is optical, green is 4.5 microns, and red is 8 microns. The blue circle that's here is the target position, and the red X's are sources from the 2MASS point source catalog. Now, the first thing that they're telling you that they want you to take away from this figure is that the target position is 2 arc seconds from the source taken as the 2MASS match. The next thing they want you to take away is that there is complex, long wavelength emission here. That's certainly true. 8 microns is red, so all that red stuff is really mostly in 8 microns. Then they say photometric measurements greater than 10 microns, combine flux densities from more than one source, because there's several sources in there, and the nebulosity. And so the reason they're including this figure is we have left this source in the set of sources likely subject to source confusion, because certainly there is source confusion in this figure. So after you've looked at the figures, you should have a sense if you really need to read the paper very closely, or if all you need is the data, or you can just recycle the paper. So we'll first go through how you do a deep dive into the contents of the paper, and then we'll talk about how to do data harvesting. So for a deep dive, you want to go back and read the introduction. On your first pass through, you probably can skip the sections on data acquisition and reduction, because those are usually quite technical sections, and until you really get into it, you don't need that kind of detail just yet. Then you can go read the discussion and the conclusions of the second half of the paper. That should be the meat of the science that they're trying to do. You are going to have to go back and reread sections. I find that I have to make notes, and rather than making notes in a separate piece of paper, I just print it out and I highlight, I scribble, I circle, I write question marks, I draw all over it, because it helps me when I go back and read it again to understand what I was thinking the first time. If you're still really interested in what's going on, then you go back and reread the data acquisition and reduction section. And you're looking for things that you don't understand, or that things that are important for how they interpret it. So if they say in the data reduction, we added a linear, we subtracted a linear fit from the data, but then later on they say, oh, look, it matches a linear fit, then that's a circular argument, right? So you want to look for things that they're doing to the data that are going to affect their conclusions, but you're also looking for details that you can learn from. So what would happen to my data if I did what they did? You probably are going to need to read different sections multiple times. And it might be the case that that no amount of reading will make it clear, because not everybody can write, and sometimes the refereeing and the editorial process doesn't catch that. So don't worry if you don't understand every single word. You should understand most of it. You should understand the essence of what's going on, even if you have to read it 10 times to get there. But there might be some things that are just completely impenetrable, because at the end of the day, some people can't write as well as we would like. So if you're just trying to get the data out of it, you have your paper, read the introduction, and decide if their goals, if their science goal is similar to yours. And if that's the case, you probably want to read it more closely. If you are just trying to get the data out, you want to look for whether or not the region that you care about or the object that you care about is truly discussed in this paper, if there's data for this object included in this paper, or if it's just mentioned in passing. So for my goal of looking for young stars, you want to look for, does the paper talk about point sources, which is what we want, or are they talking about extended emission? We don't care so much about the extended emission. You want to know if the paper is dealing with X-ray, optical, or infrared point sources, which is good, or if it's talking about radio and submillimeter, not so much. It might be important for some sources. It might be important if they're talking about point sources. It might be important for nomenclature, but in terms of understanding the specific young star point sources in the region, radio and submillimeter is less important. You also want to decide if the paper is really about primarily your region that you care about, or it may be that your region just comes up near the end. In other words, this region that they're talking about is compared to your region at the end. If the paper is at that point only seeming peripherally relevant, you should also look to see if it's giving you more references, more trails of breadcrumbs to chase that could give you more information. So if in the case where it's comparing a cluster to the region you care about, maybe they say in the text something like comparing our cluster to the results on your cluster from this other paper. Let's go check that other paper. So if the paper does seem to have substantial data that you need, go look at the tables. If it has complete catalogs, you have hit the jackpot, you win. More often the case, they're just going to give you a list of particular objects that they focused on. So it might, for example, just be a list of the young stars they found. A thing to remember is that in this era of mostly digital paper distribution, mostly digital article distribution, often big tables are not completely printed in the PDF version of the article because nobody is going to scan that huge table by eye. They're going to want data that they can read into the computer and manipulate for their own devices. So in the American journals, Astrophysical Journal and Astronomical Journal and all of their supplements and letters and all the rest of it, frequently they will only give like the first 5 rows and then it'll say, this table is included in completeness in the online version of the journal or something to that effect. And usually that means that you can get just a regular plain text ASCII version of the data. For astronomy and astrophysics, the European journal, I have found that sometimes they don't even have a placeholder for the table. And you have to read the text closely to really get, table 3 is only available in the online version of the article. Okay, So I find that a little frustrating. I find it easier when there is actually a table to look for in the article, even if the most of the table is electronic only. At least when you're scanning the article quickly, it's easy to find the table that you care about. Then you need to find in the article the text that's describing that table and find out what is included. It may be that the table includes pointers that you can follow up to get more data. So, for example, it might say, we included optical data from Smith et al., but our table 6 is only the infrared data. Okay, let's go get the optical data from Smith et al. Or they might say the spectral types are coming from this other paper. Okay, go chase the other paper. Then you want to download the ASCII versions of whatever table you can find. Almost everything these days is machine readable in, just plain ASCII, plain text format. Just, download it, keep it. The way that I manage this is I make a directory for each paper, and I put a copy of the paper, the README that comes with the tables, and the data tables I get. And if I have to modify the data tables to make it easier to read it in, I put those copies in that directory too. And then I also put the code that I'm using to read in the tables in that same directory. So it's all together. So that if I need to backtrack and wait a minute, column 3 cannot possibly be this channel's magnitude because it's just wrong, right? Then you can go back to the source. You can go back to the paper itself and try to figure out, what's wrong, figure out where the errors are. Now, you could just toss the paper on the pile and move on to the next paper that you're scanning quickly for data. But before you drop it, it's probably worth scanning the discussion section, at least the headers, and look for discussion that's important. So for example, for the example of studying young stars, maybe there's a section on how they're using the data to estimate ages or distances. That's super important. Or maybe they've decided on a story of how the star formation progressed through the cloud. That's important. So go and look for those kinds of sections and read those kinds of sections closely. If you just are in data harvesting mode, stick a Post-it on the paper or right on the top, read section 3 later, something to capture the fact that there's some more useful information on the paper beyond just the data. So eventually, when you go through all of this, you're going to have a set of papers that have really relevant data and a larger pile of papers that have only peripherally relevant data. The ones that have the most relevant data, you really should go back and read closely. You're going to have to think about that, especially when you're doing your own analysis, because you have to be able to use the other person's data sensibly. And you're going to have to read them again when you go to write up your analysis, because you need to be able to say how your analysis improves on the prior analysis.